All right, so let's dive into three-phase circuits, guys. This is going to be a little bit of overview, a little bit of in-depth discussion. It will give you an idea of how I conduct the live training sessions. Okay, these slides, for the most part, are from the on-demand course. I've added some new content, and hopefully this will turn into a good discussion and help clarify some of the concepts. And obviously, this is just like a 15, 20, maybe a 30-minute discussion. In the live training program, we go through these concepts. Average length of my sessions on a Saturday and Sunday are about 2.5 to 3 hour long, sometimes even 3.5 hour long, right? So a lot of in-depth discussion, a lot of practice problems, a lot of homework assignments. When you walk into a session and you walk out of the session, you will feel that at least several percentage points more than what you knew before you started the session. Okay, and that's the reason why most of my FE electrical students who, even if they pass the FE exam just with the on-demand course or just with the study guide, most of them opt for the live training plus on-demand for the P power. Okay, so we're going to introduce three-phase circuits, pretty high level, and then we're going to dive into the Wye-network and Delta network. Okay, so three-phase circuits, as I've explained in the on-demand course, and even in the FE electrical, this level of detail you guys are familiar with, right? So we have three phases, 120 degree apart. A balanced three-phase network is one in which both the magnitudes, all the three magnitudes are equal, and there's a constant 120 degree phase difference. Now, this 120 degree phase difference can take the form of ABC sequence or an acb sequence. You might have heard this term in the field, that we need to switch the phases. What essentially we are doing is that making sure that if it was meant to be ABC, it is ABC, and if it was meant to be ACB, it's ACB. Okay. Now, with the three-phase circuits, there are two things. If you understand these two things, you're going to be golden. Okay. That's square root 3 and 30 degrees. Okay. It's easier said than done. Where this square root 3 comes from, where this 30 degree comes from, but that's really the core issue. Okay. And it's not a simple answer that you have to memorize, that you have to just spit out on the exam. It can take different forms, different shapes, right? And it can hurt you in several different ways. So it's a good idea to take a step back and really understand where this is coming from. All right. So three-phase circuits, single-phase circuits are fairly easy. We're not going to discuss single-phase circuits over here. It's assumed that you already know that. And if you're working in the industry, you obviously work with three-phase systems all the time, right? So there are basically four major configurations that you can have, right? You can have a Y-Y configuration, i.e. the source is Y, the load is Y. You can have a Y-delta configuration, i.e. the source is Y, the load is delta. You can have a delta Y, source is delta, load is Y, and a delta-delta connection. Okay, so these are the different configurations. Now, when you look into the three-phase circuit, right? So the Y configuration and delta configuration, these are the two most common ones. Okay. You have some weird ones as well, like zigzag and Scott T and this and that. We're not going to go there. Our Y and delta are basically the bread and butter. So you have the option of grounding a Y at the neutral, right? In fact, a delta can be grounded, a corner grounded delta. This is something that I discussed in the program. You guys have probably already gone through that. And the other ways that you can ground systems, this is not a grounding lecture. This is just a three-phase lecture, but the neutral of a Y can be grounded, right? And an ideal Y connected and an ideal delta connected. I call it ideal because in reality, the sources, each source, and we're looking at sources, I'm just showing them as voltage sources, but in reality, they will have impedance in series with them, right? So that's where the non-ideality comes into play. Can somebody tell me that when we say three-phase circuits, three-phase sources, what device we are really talking about? What do you think? If we say a three-phase source, what is that three-phase source? Any idea? Generator. Yeah. Generator is a source. Transformer just transforms the voltages. It's strictly speaking, transformer is basically an impedance, right? Strictly speaking, transformer is an impedance. It's not a source. Now, generator. What type of generator? What type of generator, guys? AC, yeah, three-phase systems are all AC. There's no DC three-phase system. But what type of generator are we talking about? Are we talking about induction generator or a synchronous generator? Quickly, there are a lot of students on the webinar. Feel free to participate, guys. I understand that you might be a little bit shy when we start the live training. The first couple of weeks, students are a little bit reserved, but then they start participating and coming up online and asking questions and whatnot. So quickly, which generator do you think? Synchronous generator, right? And some of you guys are sending me messages privately. I would appreciate it if you could share your comments with everyone. Feel free to change your name or drop your last name or whatever for privacy reasons if you like. Yeah, synchronous generator. But why synchronous generator? Why not induction generator? Can somebody tell me? We say induction machine, right? So induction machine can act as a motor and a generator? Why a synchronous generator and not an induction generator? These are the level of details that you need to understand, right? And when we go through the induction machine discussion, I actually spend a good chunk of our time discussing why we cannot use induction generators. Have you heard this term induction generator in the field based on your experience? Is there anything as induction generator? What do you guys think? Do we have induction generators? We do, but they have very limited application. Induction generators, and this is not the time and place to explain that in detail. Induction generators have a limitation. They cannot provide reactive power. Okay, in fact, they themselves need to be provided reactive power by an external source in order to energize a magnetic field, right? Synchronous generator does not require magnetic field to be set up externally. It can, strictly speaking, it depending on how you start it and how you configure it, synchronous generator are actually a source of reactive power, and they can deal with both real and reactive load. That's why we actually deal with synchronous generators instead of induction generators. Make sense? All right. And then when we have loads, right, again, the loads can be connected in Y, loads can be connected in delta. When we have a balanced load, it basically means that on each phase, the loads Z1, Z2, and Z3 are all equal, okay? And then for delta, for whatever reason, they have not given this equation in the handbook for P power. This is an equation that shows up in the FE electrical handbook, and I tell my students, P power students, just to memorize this equation, right? That helps you convert a delta system into a Y system, delta impedance into a Y impedance, and vice versa, okay? So when we say that the load is balanced, we basically mean that the same impedance is showing up on every single phase. When we say that the source is balanced, it basically means that the magnitude, the sinusoids, the 3 sinusoids that are being generated by the source, they are all equal in magnitude and perfectly offset by 120 degrees. Okay, so that's a balanced source and a balanced load. Now let's talk about this 120 degrees and ABC sequence. This is something that confuses a lot of students. Well, if you plan on taking the P power exam, you better get this addressed right now. In FE, it's okay. You don't necessarily have to go in that level of detail, but for PE, you really need to get this sorted out. So when we say that the sequence is ABC sequence, what we basically mean is that our phase A voltage is going to lead phase B voltage by 120 degrees, and phase B is going to lead phase C by 120 degrees, okay? So how does this work? Our reference is the positive x-axis. This is my reference, okay? This is an underlying assumption, which is not always obvious. The second underlying assumption is that we have a movement, which is what type of movement we have. Are we moving clockwise or counterclockwise? So after phase A, we basically get phase B, right? And after phase C, it's counterclockwise, okay? So actually, this should be reversed. It's actually counterclockwise, okay? So what ends up happening is right now I'm seeing A on the positive x-axis, right? Correct? Status quo, starting at 0. Phase A is sitting on x-axis, right? I give a 120-degree counterclockwise twist. Phase B is going to be sitting over here, correct? It becomes B, right? I give it another 120-degree twist, and phase C is going to be sitting on the positive x-axis, okay? And it will keep on repeating. A, B, C, A, B, C, A, B, C. And that's basically what we mean by positive sequence, ABC sequence. Does it make sense, guys? Now, there's another underlying extrapolation from here, right? And that is that when you have an ABC sequence, the voltages, the line-to-line voltages that you're going to get are VAB, VBC, and the last one is the trickiest one, VCA. So if I tell you that the line-to-line voltages are VAB, VCA, and VBC, it should automatically click in your mind without me telling you the sequence, that the sequence he's dealing with is ABC sequence. And this will make more sense when we get to the acb-C, okay? So the magnitudes are all VM, and they're off by 120 degrees, such that A leads B and B leads C, okay? Negative sequence. Negative sequence is A, C, B. So again, we are moving in the CCW counterclockwise, okay? So on the positive x-axis, up front, status quo, before the timer starts, I have phase A. Here, when I give a 120-degree twist to it, what do I see? Phase C, okay? Another 120-degree twist, I see phase B, okay? Now, the interesting thing to note over here, let me write one more. ACB will keep on rotating, okay? So the interesting thing to note over here is that the voltages that I'm going to get are VAC, VCB, and VBA. Now, compare it. Let's compare it. So if I gave you line-to-line voltages, VAB, VBC, and VCA, you know that this is a positive sequence, correct? Without even me telling you explicitly. And there are a lot of things that, guys, you need to connect the dots, okay? You need to synthesize. You need to make whole of some disjointed facts, right? You need to fill in the blanks. You need to, complete the picture. Okay. If I just give you line voltages, VAC, VCB, and VBA, this is actually good enough for you to recognize that the given sequence is actually a negative sequence or an ACB sequence. Is that clear? Okay. This is a level of depth that we need to go into for PE Power exam. Now, do you expect that the handbook is going to explicitly mention? I don't think that they, in fact, even mention ABC or ACB sequence, right? But by changing a sequence, I can make a problem that will throw off all of your calculations if you don't grasp which sequence it is, okay? So you have to look at everything with fine-tooth comb, all right? And that's why the live training sessions for PE Power, end up being 3 hours long on Saturdays and Sundays. Any questions about this? Is this clear? All right, good. So let's take a look at the Wye-network. This is a source, right? So Wye-network, one of the things is very obvious that our phase current is equal to our line current, correct? Our phase current is equal to our line current, right? So when our phase current is equal to line current, I don't need to tell you that this is a Wye-network. You should recognize right away that it's a Wye-network because only in the Wye-network, the phase current is equal to line current. So this is easy. It really don't need to burn any brain cells understanding this. Graphically, visually, it's very obvious that the line current is equal to the phase current. What is not obvious is what's happening with the voltage. And that's what we're going to analyze. And that's where we're going to first time see the 30 degree and square root 3. Okay. So let's take a look at VAB. When I look at VAB, I understand is the difference between voltage, phase A voltage and phase B voltage. Phase A voltage, assuming that we have a ABC sequence, is going to be at 0 degrees, right? Phase A is sitting at 0 degrees over here, and phase B is minus 120, right? And the magnitude is the same. So when I do a 0 degrees minus the magnitude is the same, minus 120, right? You can express this in the form of complex numbers, right? So you have cosine. So you have V phase times cosine minus 120, right? Plus J times V phase into sine minus 120, correct? Cosine of minus 120 is going to be a minus half over here. And the sine of minus 120 is going to be minus square root 3 by 2. Okay. Rearrange this in the form of collect all the real parts and all the imaginary parts on one side. And then what you end up with is a square root 3 that can be pulled out with this, and this is basically phase angle of 30 degrees, okay? Because square root 3 by 2 is a cosine 30 degrees plus J half is basically a sine 30 degrees, okay? So this is a very profound result because what it's telling you is that the line-to-line voltage is equal to square root 3 times the phase voltage. In terms of magnitude, that's fine, but it is also going to be leading the phase angle of the phase voltage by 30 degrees. So this 30 degrees really, if you look at it, is basically angle theta of the phase plus 30 degrees. Okay, makes sense? Because over here, this was 0 degrees, right? So if this was not 0 degrees, it was, let's say it was, the phase was already at, 10 degrees. So it will become 10 degrees plus 30 degrees. Okay, so this is the math behind the square root 3 and 30 degrees. Okay, now the way we summarize it, and I think the next slide does it, the way we summarize it, we say that, okay, in terms of our magnitude, the line voltage is equal to square root 3 times the phase voltage. That's all good. Okay, but you also have to take into consideration the fact that the line voltage is going to lead the phase voltage by 30 degrees. And that's why we add the angle 30. And really, to do it properly, it's phase angle plus 30 degrees. Okay. And you can write this equation for VAB, for VBC, and VCA, all right? By taking into consideration that phase A is 0 degrees, phase B is minus 120 degrees. So this minus 90 is really minus 120 for phase B plus 30 degrees. This minus 210 is really minus 240 degrees plus 30 degrees for VCA. Make sense, guys? And then in terms of phasors, we can express it like this. So if you're considering phase A as a 0 degree reference voltage, then VAB is leading it by 30 degrees. And you can see that this phasor is square root 3 times bigger. All these turquoise blue phasors are actually bigger, square root 3 times with respect to their phase voltages. Okay, so you can just look at the formulas that are given in the handbook, rely on them, or make an extra bit of effort and derive these at least once. Okay, I think it's worth going through this derivation at least once. I think it's worth creating these diagrams at least once, the phasor diagrams at least once, so that at some part of your brain you can actually you'll feel assured that I've done it once, and I know if push comes to shove, I can work through the phasor diagrams and deal with diagrammatic type of problems on the exam and this and that. Make sense? So this is your Wye-network. Okay. Now, In terms of we can have the neutral connected. We can have the neutral brought out, right? So this becomes on the load side of things, this is VBC, phase voltages between the different lines, line-to-line voltages. And then we can also have VCN, right? Between the phase and the neutral, VBN between phase and the neutral, VAN between the phase and the neutral, and so on and so forth. Okay. So when it comes to the line currents, they are equal to the phase current. Okay. When it comes to the line-to-line voltages, it's a little bit trickier. Square root 3 comes into play over there. With the Wye-network, that's where the square root 3 and 30 degrees come into play. Okay. The line current and phase currents are all equal. All right. So here's a practice problem that I've already solved in the on-demand course, right? I'm going to go through this briefly with you guys. Another tip that I like to provide my students, tell my students, encourage them, is to sketch circuits out. I am a big proponent of visualization, right? In a field even like engineering, electrical engineering, where a lot of things are very abstract. If you talk to a mechanical engineer and chemical engineer and civil engineer, they might be able to provide 2 cents to a mechanical engineer will probably have a little bit of an opinion about some civil work. A civil engineer will have probably a little bit of opinion about something that a mechanical engineer is doing. And chemical engineer will probably have a little bit of opinion about mechanical. When it comes to electrical engineering, everyone shuts out. If you guys work in a multidisciplinary environment, you can probably relate to that, right? When it comes to electrical engineering, nobody has any opinion, right? So you guys should have opinion about electrical engineering because that's your job. No one can come and rescue. Okay, it's very abstract, but despite it being very abstract, I still recommend my students to actually go through and sketch things out as much as they can. If you've gone through my FE program, I like to sketch things out. I tell my students, take 10 seconds, 15 seconds, 20 seconds, to sketch out what the problem is asking and then work through it. It will save you a lot of time down the road. Okay, so if you look at this problem, we have a 3-phase balanced Y-connected load. Okay, and this is the phase, this is the impedance on each phase. So that basically means that this is 20 plus 5J ohm, and this is really a very easy problem. In the full-blown live training session, we go through so many different variations. Okay, it's a positive sequence. Now you guys know what positive sequence is, right? Everything is ABC, right? And the source VAN, notice that VAN phase A voltage previously had a 0-degree phase angle, not anymore. I'm giving you a 30-degree phase angle, right? So this is 120 volt with a 30-degree phase angle. Okay, now calculate the phase current IAN. Now, one of the things that I like to hammer on and on and on and on in the live training, especially when we're doing the 3-phase circuits, is that, guys, we should always try to convert everything into YY. In fact, if there's one takeaway from the entire live training session, and we have detailed discussion because I do 3-phase per unit in symmetrical over the same weekend, and there's a lot of overlap between them. If there's one thing that you need to understand is that whenever you're dealing with 3-phase systems, bring them into a YY system. Why? What's the reason? Why I'm so hell-bent at converting everything into a YY? Because when you have a YY configuration, you can look at each phase individually as if it is a single phase setup. You have a neutral here, you have a neutral here. Okay, whether it's brought out or not, it doesn't really matter. I can convert this into a single phase circuit. I can convert this into a phase voltage connected in series with the load. Okay, and this simply becomes a Ohm's law. Ohm's law in complex domain because we have phase angles to work with as well. So my current IA is simply equal to VAN divided by ZY. That's it. And that's why we love Wye-network. Okay. So it's a one-step process. And please handle the phase angles. Don't just discard them. Okay. A full description, I can give you 2 options. For example, I can make, or in fact, 4 options on the exam for that reason. All of them are going to have the same magnitude. Let's say 5.82 ABC. D 5.82. And if you were just looking at the magnitudes, you're going to fall short because you did not handle the phase angle. The angles are different. This is theta1, this is theta2, this is theta3, this is theta4. If you took the shortcut while solving this problem, you'd have to redo the problem by taking the phase angles into consideration. So a tip for you, suggestion is, whenever you're dealing with 3-phase systems, single-phase systems, transmission lines, in fact, anything, always include the phase. There's only one exception. Can somebody tell me where we don't include phase angle quickly, especially those of you who have been using the on-demand course? There's one exception. It'd make me very happy if you actually mention it. Anyone? There's one calculation where we don't use phase angle. Okay, you guys are being really shy. That is voltage regulation. Okay, in voltage regulation calculations, we only use the magnitudes. All right, so that was a quick run through of Wye-network. And in the live training, we actually have at least 3-4 practice problems to work through, all different configurations, Y delta, Y delta, and so on, especially after having completed the delta. So let's take a look at delta. Delta is different, right? Obviously, it's a closed loop. So the connections, when you get to the transformer lecture, I go through the transformer connections in detail. But let's take a look at it from the source standpoint. So the first thing that stands out to me is the fact that my V phase is equal to the line voltage. What is the line voltage? Line voltage is the voltage that is appearing between these two terminals, right? And that happens to be the phase volt, okay? So the easy thing is that the line voltage is equal to phase voltage. The easy thing in Wye-network was the line current was equal to the phase current. Okay, all right. So my VAB is equal to V phase. My VBC is equal to V phase minus 120, right? So the positive sequence. So that's all good. We've discussed that. Now the line current is actually a little bit different. Okay, so the line current, we have to explore it in a little bit of more detail. Okay, so the phase current is actually identified. This is another thing that students get confused in delta network, guys. In delta network, please listen carefully. The phase current is actually identified as IAB. Okay. Now, students are more familiar with the line-to-line voltage VAB in the Wye-network, correct? You got to pay attention here. Okay. They look at IAB in the delta network and they misinterpret it as a line current. IAB is equal to the phase current. IAB is the delta phase current. IA is the delta line current. IB is the delta line current. IC is the delta line current. Over here, VA is the Y phase voltage. VB is the Y phase voltage. VC is the Y phase voltage. Okay. So when I'm saying IA, IB, IC, the tables have turned. These are line quantities. Okay. And these are phase quantities. Okay. This is right. So you have a question, Badrish? Yeah, 0 minus 120. So it's ABC sequence, right? ABC sequence. AB comes before BC and BC comes before CA. Okay. All right. So this, I generally use stars in my live training sessions to indicate pitfalls. I didn't get a time to sort of update the slides with those, but these ones. But this is a very common mistake. And exam questions can exploit it. They can test you on them, right? So is this clear? Notation, very critical. Okay. All right, so we know that when we are dealing with delta network, the square root 3 and the line to phase relationship, because the line voltage is equal to phase voltage, so that's easy. It's a slam dunk, right? Just like in the Wye-network, we had the line current equal to the phase current. We really didn't even bother about it, right? But when it comes to the voltages, we need to bother about them, right? Why? Because in the Wye-network, we had to do the calculations. In the delta network, we have to do the same calculations, but in the context of our currents, okay? So line current, IA, is actually equal to, you can see it's IAB minus IC. So if I write a KCL, and you don't need to memorize it, if I write a KCL over here, okay, let's call this X. IAB is coming in, right? And I'm going to put that on the left-hand side. And which currents are leaving? IA plus ICA. Everyone can see that? I'm going to put them on the right-hand side. So this is my KCL. Sum of currents coming in is equal to sum of currents going out, right? What am I after? I'm after IA. So I'm going to write this IA is equal to IAB minus ICA. Good. And that's what it is. Okay. So IAB is going to have the same, we are assuming that we have resistors on the load side. So the phase angle is going to be the same as the source, right? If I had an inductor, then it would be 90-degree phase shift. If I had a capacitor, on the load end, it's going to be a 90-degree phase shift. But let's assume we have resistors. So we are not making it even more difficult than it needs to be. So IAB will have a 0-degree phase angle, right? And ICA will have a 240-degree phase angle, right? And when you do the math, right? So when you do a cosine of 240 plus a J sine of 240, you're going to end up minus half for cosine 240. This is minus half, and this is square root 3 by 2. Okay, I'm going to do the same thing. I'm going to pull the square root 3 outside, leave everything inside. And then what I find this time around is that I'm left with this. And this is basically cosine minus 30 degrees. And this is sine minus 30 degrees. So that basically means that the phase angle relationship is minus 30 degree this time. Now, this is super critical, guys. And that's why I have this in big black, bold. This is not given in the handbook, okay? Two things. First of all, when we're dealing with delta network, the thing that really throws a wrench in the system is not the voltage, it is the current, okay? And the current is interesting because previously we had the line voltage in the Wye-network leading the phase voltage by 30 degrees. So it was a plus 30 degree phase angle. Over here, it's a current, line current, and it lags. It does not lead, it lags the phase current by 30 degrees. So what we end up with is that phase A is equal to minus 30 degrees. And this is minus 30 because it's 0 degrees minus 30 degrees. This is minus 120 minus 30 degrees. This is minus 240 minus 30 degrees. Okay, this is not obvious. You cannot deduce it on the day of exam looking at the hand. And this is where the 360 degree angle, coverage, whole 360 degree review comes into play. This is where getting into the nuts and bolts of things pays off. This is where PE Power exam is very different from FE Electrical. My students who go through my FE program and then graduate to the PE Power program, when I have a one-on-one Zoom call, and you guys know I have one-on-one Zoom calls with everyone, I tell them, listen, we need to have a mindset change. In FE, you were able to get things done by having fundamental understanding, basic understanding. In PE, we really need to dig deeper, right? And those of you who are already going through the exam preparation, you would probably recognize it. If you failed the exam once or twice, 9 out of 10 times, that's the reason. You might have been trying to crack the PE Power exam by, taking the plug and chug approach. I'm not saying that you would not have studied hard. You probably would have studied even harder than the students who take the nuts and bolts approach, right? But yeah, so we really need to have a learning mindset, right? This cannot be deduced from the formulas that are given in the handbook. You really need to work through this, right? A tip is delta is focused on voltage. Current. Y is focused on voltage. The equation for Y is given in the handbook. So change everything from Y to delta like this, okay? We were dealing with line voltage in Y. It was leading phase voltage by 30 degrees. Now we are dealing with line current. Flip the line voltage to line current. This is delta. This is Y. It is lagging the phase voltage in the Y case. Now it's the current by 30 degrees. Okay, if you want to memorize it. I think this is the best way that I was able to come across. So I actually try to explain this to the students. I would rather have you go through it at least once, but then if you want to memorize it, this is how you can memorize it. Make sense? Okay, is it clear? All right, very good. Now we can look at it from the load side as well. We are running short on time. I have a few other things to discuss with you guys, but if it's a balanced load, we can connect the balanced load and we can convert the delta load into a Y connection as well. It makes our calculations easy. I don't think we're going to touch on the delta Y conversion in the interest of time, but when we convert the delta to Y, one thing I want you guys to understand, students have this confusion all the time. They're like, okay, what happens when we convert it into Y? So imagine I'm converting this into a Y network. This is a Y network, right? And the loads, actually, let me draw it. So this becomes ZY. I just showed you the formula, how we convert Z delta into ZY. And this will unlock another mystery. What was that formula, guys? Can somebody tell me? Z delta is equal to 3 times ZY, correct? Or is it the other way around? Z delta is equal to 3 times ZY, right? I'm quite sure. I don't rely on memory. Where was it? Yeah, 3 times ZY. Okay. So Z delta is equal to 3 times ZY. So that basically means that ZY is equal to 1/3 of Z delta, correct? Make sense? Okay. Now, students get confused. They're like, okay, you converted the impedance into from delta into Y. What happens with the calculation, right? In reality, we are not physically going out and converting the entire delta network into a Y network. What happens? Can somebody tell me okay, let me ask you this question. Which parameters are going to remain unchanged when I do this conversion? Whether I do this conversion on the line side or the source side, on the source side or the load side, which parameters are going to remain constant? What do you guys think? The answer is right there. It's on the screen. More specific. Obviously, we are dealing with only two parameters. It will be either voltage or current, right? I want you to be more specific. What type of current and what type of voltage are going to remain constant? Because think about it, okay? I draw a black box around it and I converted this into a Y network, correct? And same thing on the source side. So I draw a box around it and convert it into a Y, correct? So the correct answer is that the line quantities remain unchanged, I line and V line. And that is the reason why we love line quantities in three-phase systems. That is the reason why whenever you see, because I'm doing these modifications on the terminals, right? On the source terminal and the load terminal. I'm not doing any changes on the line parameters. That is why when we're dealing with three-phase systems, guys, if the voltage is not mentioned, right, by default, it is considered to be line voltage, right? These remain constant. And through practice problems, I worked through these in the live training in more detail, but that's basically the idea, right? When I convert this into a Y, and on the source side, I convert this into a Y, now my line quantities are gonna remain constant, and essentially I can convert this into a single phase circuit, okay? And once I know the Y and the line quantities, I can use the line quantities, and then I'm gonna say, oh, by the way, I have a delta on the source side, right? So I know the relationship between the line current of the delta and the phase current. So I'm going to quickly go back here. I'm going to say, okay, you tell me the line current, right? I was able to figure out what the line current was, right? Because I converted these black boxes from delta into YY, correct? You guys are following me? And I was able to solve for the line quantities, the line voltage and the line current. Now, if this was a delta network, I'm going to use this relationship and convert this line current into the phase current and convert the line voltage into the phase voltage. And if this, let's say, was a delta Y configuration, and I'm going to say, okay, I have my line voltage and the line current. Now I'm going to use this and go to my Wye-network. In my Wye-network, my line current is equal to phase current. So I'm going to leave that as is, and then I'm going to do whatever modification I need to do with the voltage. So that's the beauty of the line parameter, okay? And that's why we are obsessed with line currents and line voltages in three-phase networks. Does it make sense? Is it clear? But you need to connect the dot. You need to know what your original network was. Was it a delta network? Was it a Y network? Okay. All right. So this was a high-level overview. Still, I think we ended up spending like 30 plus minutes, and you can only imagine what we discussed in a 3-hour-long session, right? Tons and tons of practice problems. You know, there are a whole bunch of practice problems we work through. Discussion students have, questions that they have. Some students solve things differently, and then we review them in detail.